Hello, dear students. Welcome to Nuclear Physics 1, lecture number 6. I'm Dr. Pervez Ahmed. In this lecture, again, we will continue our discussions on the basic concept for nuclear physics. So, the basic concept that we will cover here at this particular lecture include the concept of nucleus, proton-neutron hypothesis, nuclear terminologies, and major properties of protons and neutrons. So let's proceed towards today's lecture. So first of all, the first terminology that we will discuss is the nucleus. So a nuclear species characterized by a total number of protons in the nucleus uh, is the number of electron in the case of the atom. This is it's the nuclear species that we can say that the charged particles that we have inside the nucleus is the only the protons, and we remember the number of protons inside the nucleus is the same as the number of electrons in the atom. So the nuclear charge is equal to uh, positive Ze. The nuclear charge we normally represents by this sign, that is positive, and Ze. So what is mean by Z? So here Z is called the atomic number, and E is the magnitude of the electronic charge. Therefore, the electrically neutral atom should have Z number of negatively charged electrons. What it mean? It mean to say that an atom by itself is electrically neutral. What it mean? It mean that it contain equal number of proton in the nucleus and number of electrons in the outermost shells, and different outermost shells outside the nucleus. So it's an atom normally contain equal number of the electrons and different orbit outside the nucleus, and the same number of the protons inside the nucleus. That's why we say that an atom is electrically neutral with respect to the charge. So atomic nucleus contains protons and the neutrons, and a particular nuclei were represent with the symbol capital X with a subscript Z and a superscript A. So now here the X, it represents the nuclei, while the Z refers to the number of protons, that also refers to the atomic number, and A is equal to proton plus neutron, and it stands for the mass number of an element or in an atoms. Neutrons, just like you people know that from your knowledge of basic physics and your elementary school, that is neutron were discovered by Chadwick in 1932. The typical experimental arrangement that was utilized by Chadwick is shown here. We have polonium source, polonium's alpha source. Chadwick bombarded alpha particles from a polonium source on a beryllium target. He observed that he observed the emission of mass-3 particles that he represented are shown here with the alphabet Y, and this Y, this was part of the mysterious particles. It has a mass equal to that of the proton, but with the no charge. With no charge, just because these particles don't have any charge, so it was given the name of the neutron. The detail of the experiment you people have already studied in your basic classes, so no need for further explanations of the Chadwick experiments. So now after the discovery of the neutrons, a nucleus has Z number of Z protons and A minus Z neutrons. So has the proper total mass and charge. So without the need to introduce nuclear electrons. I mean, now we can completely define the nucleus. That nucleus has Z protons and A minus Z neutrons, and this is the proper total mass and charge of the nucleus. And here we don't need to mention about the nuclear electrons that also uh, we call the beta negative, or we can call we can also mention something about the beta positive, which is called the positrons. uh, Proton-neutron hypothesis in 1932. So basically what we have uh, inside the nucleus, just like I mentioned, we have proton and the neutrons. So the combined mass of the proton plus neutrons is basically called the atomic mass of that particular atom or element, and that we represent by A. Similarly, the atomic number uh, that we represent are that we represent by capital alphabet Z, and that is equal to the number of protons in the nucleus, uh, and R with the number of the electrons in the outermost shells of an atom. Uh, A minus Z is basically the number of the neutrons, that is the particles, the neutral particle inside the nucleus, that we can also represent with the English capital alphabet N. And the nucleus is represented as, that is with the capital X with the subscript Z and superscript A. So we can have a good example for that. For example, we have uranium 238 nuclei nucleus. So here A is equal to the atomic mass equal to 238, and U has number of protons or charge that we represent by Z, and is equal to 92. That is the number of protons equal to 92. And by this concept, if we subscribe from atomic mass we subscribe the number of proton, so we will left with the number of neutron, which in this case equal to 147. Now let's proceed toward some relevant terminologies. So the first terminology is nucleon. What is mean by nucleon? By nucleon we means protons or neutrons inside the nucleus. I mean the number of protons or neutrons that contained by a nucleus are normally we call them as nucleons. Nuclide, what is mean by nuclide? So nucleus are uniquely specified by N and Z. Isotopes, what is mean by isotopes? So from isotopes we mean nuclei with the same atomic number, that is with the same number of the protons. So with the same number of protons but different numbers of neutron. An example of that is protium, deuterium and tritium. So all these hydrogen isotopes, they have one protons but they have different number of neutrons. I mean here protium has no neutrons, deuterium has one neutron, and tritium has two neutrons. Isotones, so isotones are basically the nuclei with the same number of the neutrons, and the example of with the same number of neutrons but different number of protons. So example of that include deuteriums and helium-3. So deuterium contain one protons and one neutron, and helium 3 contains two protons and one neutron. So isotone has the same number of neutrons but different number of protons. Isobars, so isobars it include the nuclei with the same atomic mass. So example of that include tritium and uh, helium-3 again. So these are the sort of the nuclei which have the same atomic mass. They are called isobars. atomic mass unit. So one atomic mass unit, we already have the detailed discussion about the atomic mass unit and lecture number first and second. So here we just will just mention about the atomic mass unit. The one atomic mass unit that we represent by U is equal to 1.66 and to 10 raised to power minus 27 kg, which in term of energy unit is equal to 931.5 mega electron volt per c square. So these were some terminologies with the uh, uh, with respect to the nucleus or with respect to the nuclei. So now we proceed toward the core structures of the protons. So it's you can see here it's the core structure of the protons. So I mean these are the three different quarks that's been contained by the proton. Protons basically contain two up quarks and one down quarks. So here's the majority properties of the protons. That is, proton is being classified as baryons in the group hadrons, which been called fermions. Compositions of the proton include two up quark, which has a charge, I mean, it's a fractional charge equal to positive 2 or 3, and one down quark with the charge equal to minus 1 by 3. Interactions that basically, the proton field include gravitational, electromagnetic, weak, and strong. I mean, these are sort of the interactions which the proton can do. I mean, proton can do the electromagnetic interactions, gravitational interactions, weak interactions, and strong interactions. The antiparticles of the proton is called antiprotons, which have the same mass like the proton but with the negative charge. And we remember proton was discovered by Ernest Rutherford in 1919. Mass of the proton is equal to 1.672621637 and to 10 raised to power minus 27 kg, which in term of energy unit equal to approximately 938.3 mega electron volt per c square, which in term of U is equal to 1.00727646677 unit atomic mass unit. Mean lifetime of proton is greater than 2.1 in 10 raised to power 29 years. Sorry, it's mean that proton is a stable particle. Charge of the proton is plus 1 time the charge of the electrons, that is equal to approximately 1.6 into 10 raised to power minus 19 coulomb. A charge radius of the proton is equal to 0.877 femtometers. Electric dipole moment is smaller than 5.4 into 10 raised to power minus 24 electron centimeter electric. Polarizability is equal to 1.2 0 into 10 raised to power minus 3 femtometer cube. Parity is equal to plus 1. Magnetic moments equal to 2.79284731 a nuclear magnetic moment. Magnetic polarizability is equal to 1.9 in 10 raised to power minus 4 femtometer cube. The spin of the proton is equal to 1 by 2 and iso spin is also equal to 1 by 2. The quark structure of the neutron basically consists of one up quark and two down quark that you can see it here. Major properties of the neutron include that it's been classified as a baryons and the hadron group that's called fermions. The compositions of the neutrons include one up quarks with a charge equal to plus 2 by 3 and two down quarks with a charge equal to minus 1 by 3 each. Interaction that feel by the neutrons include gravitational, weak, and strong interactions. The antiparticles of the neutrons is called antineutrons, which also are baryons. It's a baryon number equal to -1. And neutron is being discovered by James Chadwick in 1932. Mass of the neutrons is almost same that of the proton, and is equal to 1.67 into 10 raised to the power minus 27 kg. That is equal to 931.5 mega electron volt per c square, which is equal to 1.00866 atomic mass unit. A mean lifetimes of the neutron is equal to 885.7 second. For this duration, it's been free. After that, it's been decay into the proton. So it's mean that a neutron is not a stable particle as compared to the proton. So charge of the neutron is zero, or we can say that neutron has a net charge equal to 0 at 0 degree centigrade. Electric dipole moment is smaller than 2.9 in 10 raised to the power minus 26 centimeter. Electric polarizability is equal to 1.16 in 10 raised to the power minus 3 femtometer cube. Parity equal to +1. Magnetic moment is equal to minus 1.9 nuclear magnetic moment. Magnetic polarizability is equal to 3.7 into 10 raised to the power minus 4 femtometer cube. Spin of the neutron is equal to 1/2, and ISO spin of the neutron is equal to 1/2, or you can also call that half. So that's all we have for this lecture. Hope you have learned a lot. Uh, Stay tuned with the next lectures. That will be lecture number 7. In that lecture, we will have discussions on nuclear units and dimensions. So stay tuned with the next lecture. Till then, bye bye.